All right, welcome. In this video, I want to talk about an artificial life research project that was carried out in the early 90s. It was called Tierra. And Tierra was created by this gentleman here, Tom Ray. He was and is an ecologist. As it says here, he developed this artificial life simulation in 1992. So that was right in the early days of artificial life. He carried out this research work for a number of years, and he published a couple of interesting papers on it. I want to use his research to just explore how artificial life works, and this again is just an example of one experiment, but it's a really interesting one. So to start out, I want to kind of describe kind of how the broad strokes of how the Tierra environment works. So the Tierra environment is an environment where the living organisms that we're going to study are actually computer programs. Now, I've got an example of a computer program here that I'm going to talk about here in a second, but I do want to say that this example program that I got here is completely made up. I made this up for the purpose of illustrating this Tierra artificial life experiment. In the actual Tierra experiment, the living programs were more complex than I'm showing you here, and they were written in a special dedicated assembly language, which would take a little bit of time to explore in a lot of detail. So instead of doing that, I'm going to just wave my hand at that and sort of say, if you're interested, you can go check out in more detail. But for now, I'm just going to make up an example that's kind of similar, has similar properties, but it's a little bit simpler to understand. So let's imagine we've got a simple program here. I'm calling it living program for a moment, just to give it a name. And we can imagine it's just got a whole bunch of operations inside of it. Some of them are no ops or do nothing, so they just do nothing. They just take time on the CPU. Others might do something, but what they do is maybe not super relevant to our discussion. Maybe they increment some variables that are not really relevant, or they change some memory somewhere that's not important to this program. Whatever it is, it's some other operation that's not super important to this program operation. When I say it's not important to this program's operation, it's obviously part of this program's operation, so it's obviously doing something. But what I mean is the key parts of this program are the parts that copy itself, because this is an artificial life program, and what's interesting is if it can copy itself. So I've highlighted a couple lines in here. Maybe there are a couple variables that are inside these programs, and again, Tierra was set up with special rules so that a program might be able to refer to itself, quite easily. It doesn't have to guess where it is. And for instance, it might initialize its copy pointer. So assuming we have a pointer that it tells you what it wants to copy to line X, and maybe line X is the first line of this program. Okay, so maybe by default, these programs know that I'm going to set it up, so I'm going to start copying myself from the beginning of my program. Okay, now of course, we could imagine different programs that started copying somewhere else, and we'll think about that a little bit more in a moment. But for the moment, let's assume line X is just the first line of this program. Now, we're also going to have a destination pointer, so if we're going to copy something, we have to copy it from somewhere. That's the copy pointer. We need to copy it to somewhere. That's the destination pointer. And again, let's assume that there's built into Tierra some simple way of finding some free memory, not just free memory, but free memory maybe big enough to copy myself if I needed to copy myself. And that's what this line is going to do. It's going to move to some other point in memory. And I haven't mentioned this yet, but I've sort of visualized memory off to the left here. It's empty right now. It's a bunch of gray, empty cells. But maybe this one program lives in memory, and it lives right here. And I've sort of just referenced that as this green block here. So now imagine we have our copy pointer maybe set up to the beginning of our green block, our destination pointer, while we've just picked somewhere else in memory that we have free space, plenty of free space in this example. And then maybe again, there's some other do somethings that happen, but at some point in my program, I'm going to have a copy loop. Now, we can imagine that this copy loop was hard-coded in by Tom Ray at the beginning of his simulation. Now that was not true for all the programs, I don't believe, in his original program. But we can imagine for now, at least for our example program, that there was a copy loop built in there. And I've made it fairly simple. It just says begin copy loop, and it does, does this loop, copy the copy pointer to the destination pointer. So we can imagine that copying the first line somewhere and then advance them both, increment, boom, the loop goes on for a while, it copies the whole thing. Well, we'll assume for this program that it is a good copy loop, so it copies the whole thing and then it stops. So maybe the begin copy loop here tells you how many lines it's supposed to copy before it stops. Okay, so those are the things that we can imagine are built in here. Again, there are other operations that might be useful to some programs at some point, but for now we're just going to assume that this program has this setup. It's got some operations that may or may not be useful but don't seem to be super important, and then it's got some operations that are set up for copying itself. Okay, so to get started, what Tom Ray actually did is he just initially populated memory with random programs, and I haven't filled up all memory. I just imagined saying, okay, we generated some programs that were kind of random. The language and how we build these random programs are set up enough that we should expect that at least some of the programs that we create are what I'll call viable, meaning they're capable of copying themselves. If all of the programs are incapable of copying themselves, which is certainly possible if you're just randomizing some programs, they almost certainly wouldn't copy themselves if you just randomly generate them. So there must be some way built into Tierra ahead of time to ensure that some of these programs are going to be viable while maybe some of them are not. So the way I've visualized this here is my two green programs here, I'm going to assume are the viable ones that can copy themselves, and the light gray programs that I've introduced here are ones that do something, we don't know what, but they certainly don't copy themselves, and so they're unfortunately unviable, which means after a while they're probably going to die off. Now, I haven't really mentioned how so this is a visualization of memory, but how does the CPU work? Well, the visualization of the memory here, that's where they live. But for the moment, this wasn't exactly true, but for the moment we can assume that each of these programs has its own little processor, so it gets to run on it. It's just maybe they're all running in parallel. Again, that's not exactly how it worked in the original Tierra. They all ran in serial, but they all got a time slice to balance it off, so as though they were all running on their own CPUs. Now what that means is shorter programs run faster, so you can complete that program faster. And again, in the original Tierra, if you had a time slice and you're done, you would just start running again from the beginning. Same thing here. We can just imagine when you get to the end of your program, you start running your program again from the beginning. So all of our programs have that ability to do so. Now, like I mentioned, some of our programs might be able to copy themselves, so I've just sort of indicated here maybe our big green program copied itself, our smaller green program copied itself, so they reproduced. But the others, the gray ones, they cannot. They're doing something, but again, whatever it is, it's not copying themselves, so that doesn't help them. So we can imagine that they're actually going to die out at some point. Now, they get a certain number of cycles before they die out. So that means they could run their program a number of times before they die out. Now, what that might leave us with are just the living programs. And you can see again here that I've indicated two kinds of living programs. There's the darker green, larger program, and then there's the smaller, lighter green program. Now that's to indicate one that's shorter, okay? Now, maybe I've got a little visualization of here. Maybe that's one that through mutation, or maybe just initialization, as we saw here, they have less of those extra operations, less of the do somethings and the do nothings, and so they don't waste as much time necessarily in copying themselves. If the main focus of the program is to copy itself, then wasting other operations doing other things is not necessarily going to help you. It's going to hinder you in the long run, in the evolutionary run, because the shorter programs will get to copy themselves faster. And if you get to copy yourself faster, in the future, there should be more copies of you than there are of another organism that copies itself slower. And so again, I've kind of just tried to visualize that here. There are more copies of the light green agent appearing in memory than there are the dark green agent because they are quicker to copy. I mentioned that our older programs die off, so I've just deleted some of our initial programs here, simulating that maybe they ran out of cycles. But over time, new programs are going to be added. So I've mentioned this already, but when these programs copy, they can mutate, or the way they mutate is by making errors in their copying. Now imagine in the copy loop, we had some kind of error that made it stop early. Then that might cut off a couple of the lines at the bottom, so that now we, through mutation, if those extra lines were useless, like I had in my original example, maybe they were do nothings or do somethings, then maybe those lines get cut out. It doesn't change our ability to copy ourselves, and now we're a more efficient copier. So we might be more advantageous in the future. Now, of course, it's possible that when we do a mutation, that some of those we might delete out some of the important stuff. We might accidentally overwrite or copy the wrong thing so that our copy loop becomes disabled, or we break one of our pointers or something like that. And for most of those programs, if that happens, then they're going to become inviable. That just means they can't copy themselves, and so even though they are a mutant that got copied and put out into the world, they themselves cannot copy themselves, and so they will not make any more copies of themselves. So for the most part, the mutants that are incapable of reproducing, they're not as important to the simulation because they usually stick around for a very short amount of time and then die off, but they are certainly present in the simulation. So if we run this problem for a while, we can see it starts to fill up with programs. So we've got this simulation going. So Tierra was allowed to run for quite a while. And we can imagine that at some point, okay, the shorter programs are faster, so they start populating more. You can see that brightest green one is sort of populating the most. And then finally, again, I've sort of maybe simulated a few generations where some of them are dying out and they're being repopulated, that you can see that after the memory starts to fill up, yeah, there are still some inviable ones being mutated. That old dark green one, the first one we started with, is sort of still hanging around. The middle one is pretty populous, but the light green one has definitely taken over and is starting to overpopulate. And if we let this run for a long time, it's very possible that all the dark green ones would get forced out, and then we'd only have these two kinds. And of course, I haven't simulated more mutations, but there's certainly room for more optimization here to delete out some of these the final do nothings and do somethings. And so we could imagine even shorter programs emerging, and a slow, improvement in the performance of these programs over time as they evolve and get shorter and shorter, and finally only have those essential lines of code in there. And imagine, okay, so say we ran it for a long time and that started to happen, and what would probably happen is the whole memory would be populated by those optimal replicators or reproducers. However, what actually happened, so that did happen, that certainly did happen in Tierra, but something else a little bit more surprising also happened. At some point, one of these inviable programs that we got evolved to be a very special kind of inviable program. And again, we might call it an inviable program, but you can draw your own judgment here in a second. So what this program evolved to do is it evolved to say, well, you can see here it's got no copy loop. But it's kind of smart. It said, I don't necessarily need a copy loop. Look at all these copy loops that are already out there in memory. There's copy loops in every single one of these other programs. If only I could just hijack the copy loop of another program, similar to a virus, how a virus hijacks the copy loop of a bacteria, then maybe I can trick that other program into copying me instead of copying itself. And so that's exactly what these little parasite programs evolved to do. So I've just got to, again, this is in my made up language. Remember, these languages don't, that's not what the real Tierra did, it's just something similar to this. So imagine it moves its destination pointer to some other program and tries to change the other program's copy pointer to itself. So in most of the programs, you would have some line that says, okay, start copying on myself, right? Well, what this parasite program does is goes out to these other programs and says, find that line where it says start copying on myself and change it to say start copying on the parasite program instead. So start, and that's the only thing that that program really has to do. It just has to go to that other location, copy its own line in there, and then let the other program do all the other work. So when this parasite program gets a chance to execute, all it's doing is going out and looking for other programs that it can infect. When the other program, one of the infected program, gets a chance to execute, what it does is it thinks, oh, I'm going to go copy. But because it's been hijacked, it copies the parasite program instead, and it goes and copies it somewhere in memory. So we can imagine what happens is over some time, that parasite program starts to take over memory. At this point, we can maybe imagine many of these normal programs are being hijacked now by parasite programs to copy and make more parasites. And eventually we might imagine, oh, gee, maybe the whole memory is going to be filled up with parasite programs. All we're going to have left is parasite problems. The interesting part, though, is, of course, the parasite programs are dependent on the real programs to copy themselves. If there are no real programs, then the parasites can't copy themselves. So what actually happens is that there's this equilibrium that emerges where there's just enough, normal self-replicating programs in the environment to, one, just keep replicating because they have to reproduce themselves, but also to do all the dirty work of reproducing all the parasites. And then there's just enough parasites in the population to not overwhelm the self-replicators. Otherwise, they would drive themselves out of or drive themselves to extinction. And in fact, what really happens is it's not a pure equilibrium where it's just perfect, is they oscillate between the two states. They would, too many parasites would go, and then that would make it so they couldn't copy themselves anymore, and then because there weren't enough self-replicating programs for them to copy themselves, and then that would give enough space for the self-replicating programs to maybe copy themselves a little bit more. Well, once there's more copies of themselves, well, the parasites say, hey, I'm going to hijack you and copy more of myself. So there was this back and forth. We call this a predator-prey relationship that follows a set of equations called the Lotka-Volterra equations that you can find some more information about, and I'm going to make another video about those in the future. But we saw that this is the kind of dynamics that happen with the parasites and the living programs, the self-replicating programs in Tierra. Now, this pattern continued in Tierra for a while, and it started an arms race, which is also very common in biological evolution, where the self-replicating programs, they could evolve ways to protect themselves. So remember, if the way the parasite program was hijacking them was that it was going in, finding that line where it moves its copy pointer and changing it to the parasite program. Well, maybe one of those self-replicating programs could evolve to set its own pointer twice. So it sets it the first time, and then it resets it again the second time just to make sure that it's set on me. And if the parasite program's not, set up for that, it will only maybe copy the first one. And now the self-replicating program is now immune to those parasites. It can copy itself all it likes because it always reasserts itself when it needs to. Now, of course, the parasites aren't going to like that. Once these self-replicating ones that are a little more immune or resistant to the parasites emerges, it's going to start taking over the environment, and all all of the old self-replicators that the parasites like to exploit are going to start to die out because the new ones are way more efficient, or not just efficient. They might not be more efficient. They might be a little longer, right? Because they have that redundant bit, but they are protected from the parasites. So they're not ever getting hijacked. So they can always make copies of themselves into the future. Now, of course, as I mentioned, those parasites they're starting to die out. Well, maybe one of those parasites evolves to double punch the self-replicating one, saying, okay, I see that you've got it in there once, but maybe you've got it in there twice. So I'm going to go in there and I'm going to find a second one and copy it over your second one too. And you can imagine this escalating into an arms race. Well, now there are 3 pointers I need to put in there. Well, now I've got 3 copiers in there. And at some point, there's going to be diminishing returns for both the parasites and the self-replicators, but more so for the parasites. If you're a parasite that needs to change a self-replicator 7 or 8 times just to copy yourself, it's probably just more efficient to copy yourself. But again, this arms race continued, and in the real world, in the biological world, when you have arms races like this, you can get some really ridiculous things. So both the megafauna of the world, that means the largest animals of the world, like woolly mammoths and saber-toothed tiger, they evolved prior to the arrival of humans through a arms race like this, which was, if I'm prey, being bigger makes it harder for you to eat me, so it's better to be bigger. And if I'm a predator and my prey keeps getting bigger, if I want to eat, I better get bigger. So both kept getting bigger, until again you get diminishing returns. The dinosaurs can tell you about that. They were enormous dinosaurs, and they had to carry around all this weight because they were just evolving to maybe not get eaten by that T-Rex, right? And so these kind of arms races certainly exist in the real world. And again, this kind of pattern was found in Tierra. So this is considered to be one of the early and exciting and interesting artificial life simulations and models. I will leave it up to you to determine if you think that these self-replicating programs, were they alive or not. Maybe go back to that last video where we talked about conditions of living systems, and maybe go look at those 7 or 8 properties and say, well, which ones of those properties actually do these programs actually satisfy? And I think they do satisfy many of them. But again, I'm going to leave that up to you. As artificial life researchers, we try to create these simulations mostly to raise questions, and mostly to pose more questions that we can ask that might help us understand both these interesting computational systems and the living systems that inspired them. So I hope you enjoyed this quick run through on the Tierra simulation. Thanks a lot for watching, and we'll see you in that next video.